Hi guys, just a quick lesson on exponential graphs. So the first thing that we're going to look at is when we plot them. Okay, so the exponential function f with the base a is defined by f of x is equal to capital A baby a to the power of x, where a is a positive constant other than 1, so a is greater than 0 and a does not equal to 1, and where x is equal to any real number and x is the indice. So for f of x is equal to 2 to the power of x, that's what it's going to look like. So just if I was to talk about an example, I've seen before a snowball waltz. So the first person comes up and they ask somebody to dance. So before the song starts, so if the time is 0 seconds, there's one person thinking about who they're going to ask. And then in the first chorus of the song, there's two people on the dance floor dancing. At the second chorus, those two people then break up and they grab a different partner each, so they now have 4 people on the dance floor. The third verse of the song or chorus of the song, those 4 people break up and they grab a new partner each, so it becomes 8 people. The fourth verse of the song breaks up and the 8 people now grab a new partner, which will become 16, and the snowball waltz goes on until everybody in the room is dancing. Okay, so that's what we're talking about, where x is the 0, 1, 2, 3, 4, and the f of x, or the solution, is that answer. Okay, so if I have my graph, f of x is equal to 2 to the power of x, 2 to the power of 0 is 1, so that's going to be my first example here. So when I plug in my x is 0, I get my f of x to be 1. 2, when my x becomes 1, it's 2 to the power of 1, so my f of x is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, go on and so forth. So if I actually look what that looks like as a graph, it looks like this here when it's plotted. Okay, so my 0, 1 is that point there, my 1, 2 is that point there, my 2, 4 is that point there, my 3, 8 is that point there, etc. Okay, so that's what it's going to look like as it's graphed. A little bit more on that. If I was to plot the following exponential functions, so 4 of them are graphed below, and we have to compare the graphs of functions where a is greater than 1 to those that are between 0 and 1 for their a values. Okay, so the purple graph there is y is equal to 7x. So again, it's the base is 7 to the power of x, so it meets the y-axis at 1, and it gets steep very, very fast with a 7 base. Okay, when I have y is equal to 2x, it's still meeting the y-intercept is 1, and it's not so steep. Okay, so 7 and 2, which one of them is steeper? The 7 is steeper, so that might be something that you need to consider. For the a, for 1 over 7 to the power of x, my a is 1 over 7, so it's less than 1, but greater than 0. My function is actually decreasing. Okay, so this is called a decreasing function. Again, if you multiply anything by a fraction, it's going to get smaller. Okay, and again, for y is equal to a half x, where my base is a half, it's a fraction, so it's decreasing, but it's not decreasing as quickly as something multiplied by 1/7. Okay, so where it's greater than 1, my graph is increasing. So when a, oops, I need my pen, sorry. So when a is greater than 1, it's an increasing function. And when a is between 0 and 1, it's decreasing. Okay. For the next lot of graphs, we've got 3 exponential functions have been graphed, and compare the graphs where a, the capital A, is greater than 1 this time, and the capital A is between 0 and 1. Okay, so for y is equal to 2x, that's kind of our parent function here, it's this blue line. Okay, if I was to look at y is equal to a quarter times 2 to the power of x, so my capital A is a quarter and my base is still 2a, so we can notice that because my capital A is a quarter, it means my y-intercept changes to being a quarter. Okay, and then it gets gradually steeper like so. When my capital A is a 4, my y-intercept is 4. So essentially, your capital A is your y-intercept. Okay, so your capital A is your y-intercept, and that's what you need to remember from these graphs. So the next thing that we're going to do is we're going to just take an example and we're going to plot it. So if I was to draw out again, I want to plot the graph of y is equal to 4 times 1.5 to the power of x for this domain here. So x is between -2 and 4, and comment on the graph's features. So first of all, I'm going to look at what x values I actually have. So x values, it has to be greater than -2, so I'll start with -1, 0, and it has to be less than 4, so I'm going to go as far as 3. So there are my x values, and then I'm going to find out my, sorry, I was going to say f of x, but it's actually given to me as y, so I'll use y. So what y is going to be equal to. So if I plug in x is equal to -1, I'm going to do 4 times 1.5 to the power of -1, and I get an answer of 2.67. Okay, if I plug it in for 0, I get 4 times 1.5 to the 0, and 1.5 to the 0 would just be 1, so 4 times 1 is 4. If I plug in 1, I end up with 6. If I plug in 2, I end up with 9, and if I plug in 3, I get 13.5. Okay, so I've now got some points that I need to plot, and I can start plotting them now. Okay, so as usual, we're going to draw our x and y axis. So all my y's are in the positive, so they go from 2.67 to 13.5. So my y values, I don't need any negatives, I just need positives. And my x values go as far as -1, like so. Okay, so that's my y-axis and my x-axis. And I'm basically just going to plot my points. So it's 0, 4, which is going to be about here. Okay, so if I'll mark off 5s. 5, 10, 15, like so. -1, 1, 2, 3, 4. And I'm going to plot my points. So my 0 and my 4 is going to go there. My -1 and my 2.67 is going to go about here. Okay, sorry, so then we've got 1, 6, so 1 is going to be just above the 5, like so. 2, 9 is going to be just under the 10, like so. And 3, 13.5 is going to be about there. So if I was to sketch that, my graph will look like that, and it will... Actually, it needs to finish because I've been given a domain. So it needs to finish when x is 3, and it needs to finish when x is -1. Okay? And that's it, we're done. So we should be able to go from there. Perfect.